Hello students, welcome to my channel Engineering Education. Please subscribe my channel. Thank you. This lecture is about the solution of problem 11.3, chapter 11, Rotodynamic Machinery, book Applied Thermodynamics by Eastop and McConkey. The statement of the problem is the nozzles of the impulse stage of a turbine receive steam at 15 bar and 300 degrees centigrade and discharges at 10 bar. The nozzle efficiency is 95% and the nozzle angle is 20 degree. The blade speed is that required for maximum work and the inlet angle of the blades is that required for entry of the steam without shock. The blade exit angle is 5 degree less than the inlet angle. The blade velocity coefficient is 0.9. Calculate for a steam flow of 1350 kg per hour, the diagram power and the diagram efficiency. So first of all, we will extract the given information in the statement. So we have given the initial condition of the steam, that is P1 15 bar. This is the initial condition of the steam at inlet, and temperature T1 is 300 degrees centigrade, while at state 2, when it discharges, the pressure becomes 10 bar. The nozzle efficiency is 95%, so the nozzle efficiency is 95%. This is the nozzle efficiency. While the nozzle angle alpha I is 20 degree. The blade speed is that required for entry of the steam without shock. Blade exit angle is 5 degree less than the inlet angle. So beta E is equal to beta I minus 5 degree. Blade velocity coefficient K is 0.9, while the mass flow rate is 1350 kg per hour. We have to find the diagram power. So two things are required in this problem. First, to find the diagram power, and second, we have to find the diagram efficiency. Represented by eta d. So these two things are required in this problem. So before starting the solution, let's discuss the velocity triangle for this specific problem. This is the absolute velocity at inlet, and this is the relative velocity with respect to the blade at inlet. This is blade speed or blade velocity. CRE is the relative velocity at exit with respect to the blade, and CAE is the absolute velocity at exit. And the angles alpha I is the nozzle angle at the inlet, beta E is the blade angle at exit, and beta I is the blade angle at inlet. From this velocity triangle, the angle OAB, if we take the sine OAB, it is equal to 180 degree minus beta I. and if we expand it, we get that sine OAB is equal to sine beta I. This will be used later on in the solution of this problem, so it is highlighted over here in the start. Similarly, nozzle efficiency is equal to the actual enthalpy drop, which is H1 minus H2, and to the enthalpy isentropic enthalpy drop, H1 minus H2S. So nozzle efficiency expression is H1 minus H2, which is the actual enthalpy drop, and H1 minus H2S, which is the isentropic enthalpy drop. So coming to the solution of this problem. So first of all, from the condition of the steam at inlet at T1 15 bar and T1 300 degree C, if we go to the steam tables, first we visit the saturated steam tables. From there we see that the saturation temperature is less than 300 degree C. So it means that the steam is in superheated region. So going to the superheated tables, from there at 15 bar and 300 degree C, we will note the values of enthalpy. So the value of enthalpy at 15 bar and 300 degree C is 3039 kilojoule per kilogram. Similarly, we will note the value of specific entropy, and that specific entropy S1 is 6.919 kilojoule per kilogram per Kelvin. Similarly, to find the value of H2S, which we need here, for that again visiting the saturated steam table, from there we see that the specific entropy value 6.919 is greater than the value of the SG, meaning that S1 is greater than SG from the saturated steam tables. So at 10 bar and at this specific entropy value, again we predict that the steam is in superheated form. So again referring to the superheated tables, from there we calculate the value of H2S, and the value of H2S from the table is 2940.5 kilojoule per kilogram. Now taking the difference of these two values, which is H1 minus H2S, so H1 minus H2S is equal to, H1 is 3039 while H2S is 2940. So subtracting it, we get the value 40, and we get the value of, by subtraction, 99 kilojoule per kilogram. Now to find the actual enthalpy drop, so for that we will use the nozzle efficiency expression. So actual enthalpy drop will be H1 minus H2, and it is equal to nozzle efficiency N2 H1 minus H2S. So nozzle efficiency is 95%, which is 0.95, and the value of H1 minus H2 is 99 kilojoule per kilogram. So from this we get the value which is 93.6 into 10 raised to power 3 joule per kilogram, or it is 93.6 kilojoule per kilogram. Now to find the value of CAI, which is the absolute velocity at inlet, it is equal to, from the nozzle analysis study, we know that it is equal to 2 into H1 minus H2. So putting the values, square root of 2 into H1 minus H2 is basically 93.6 into 10 raised to power 3. So the value of CAI calculated from here is 432.7 meter per second. So this is the value of CAI, which is the absolute velocity at inlet. Later on this value will be used to find some other missing parameters or terms. Now for maximum work we have to find the blade velocity, and the blade velocity for maximum work is equal to CAI cos alpha by 2. So putting the values, CAI is 432.7, cos of alpha I is 20 divided by 2. So simplifying this, we get the value which is 203.3 meter per second. So this is the blade velocity or blade speed. Now also to find another velocity, that is relative velocity at inlet, for that we will use the cosine law. So from velocity triangles, cosine law is used. CRI square is equal to CAI square plus CB square minus 2 CAI CB cos alpha I. We have used this expression again and again in other problem solution in the first two problems, problem 11.1 and 11.2. Now putting the values, CAI is 432.7 square plus 203.3 square minus 2 into 432.7 into 203.3 cos of 20 degree. So simplifying this and solving it for the relative velocity at inlet, CRI is equal to 251.5 meter per second. Also to find the blade angle, for that we have that sine beta I is equal to CAI by CRI sine alpha I. Actually here we implemented the cosine law, sine law, the sine law. So from this we will find the angle beta I, which is the blade angle at inlet. So sine beta I is equal to CAI is 20432.7 divided by CRI is calculated here 251.5, and sine alpha I is 20 degree. So simplifying this and calculating it for beta I, the value of beta I is equal to 36.05 degree. So now to find the relative velocity at exit, for that we have the expression that CRE is equal to K CRI. So K is known to us, which is 0.9, and the value of CRI is 251.5 meter per second. So simplifying this, we get 226.4 meter per second. Similarly, the blade angle at exit is equal to blade angle at inlet minus 5 degree as given in the problem. So beta I is 36.05 degree minus 5 degree. So the blade angle at exit comes out 31.05 degree. Similarly, to find the change in world velocity, which is delta CW, we have that CRI cos beta I plus CRE cos beta E. This is the expression for delta CW. So putting the value, CRI is 251.5 meter per second, cos beta I is 36.05 degree, plus CRE is 226.4 meter per second, and beta E is 31.05 degree. So simplifying this and solving it for delta CW, we get the value 397.3 meter per second. Now to find the diagram power, now we are able to find the missing or the required parameters or terms. So the diagram power is equal to m dot delta CW into CB. So m dot is 1350 kilogram per hour. To convert it into kilogram per second, we will divide it by 3600 seconds. Also, the value of delta CW is 397.3 meter per second, and the value of blade velocity is calculated already, let's check from the above value, 203.3 meter per second. So putting that value over here, 203.3 meter per second. So simplifying it, we get the value of diagram power, which is equal to 30.3 kilowatt. 30.3 into 10 raised to power 3 watt, or 30.3 kilowatt. So this is the value of diagram power required. Similarly, to find another term, that is the diagram efficiency, so for that we have the expression that the diagram efficiency is equal to 2 delta CW into CB by CAI square. So putting the values, 2 into delta CW is 397.3 meter per second, and CB is 203.3 divided by CAI. CAI is 432.7 square. So simplifying this, we get the value which is 86.863. In percentage, the diagram efficiency is equal to 86.3%. So this is the solution of problem 11.3. Thanks for watching. Please like and comment on my videos. Also subscribe my channel to get new videos.